Forces are very important to understand for engineering applications. They can often mean the difference between working for you and working against you. SOLIDWORKS Flow Simulation has countless uses for designing internal or external fluid and thermal systems. But today, we have a showcase explaining how flow can be used to identify forces on surfaces, such as downforce, drag, lift, pressure, and wind loading for engineering applications that can make all of the difference. Looking at a case study example, NASCAR teams at one point required airfoils on the back of all the cars that put significant downforce on the rear end. This increases traction. Unfortunately, when a driver was spun backwards on high-speed tracks like Talladega, the design was thought to have turned the massive downforce into lift because an airfoil is effectively an upside-down wing. Several drivers ended up spiraling into the air on multiple occasions and something had to be done. When creating a SOLIDWORKS flow simulation, one of the options to use when creating a goal is to create a surface goal that reports the reaction forces on that selected surface. This application is exceptionally useful because it can identify most of what an engineer needs to make a good design judgment for aerodynamic applications. In addition, the effects of the fluid can be imported into SOLIDWORKS simulation to create a force feature that can be used for finite element analysis. The newer designs greatly change the behavior of the airflow that keeps the car glued to the track by making low pressure zones underneath the bulk of the moving air. In the case of the original airfoil, it was discovered during testing that the airfoil did little to provide accidental lift, and that the majority of the lift was generated because air went underneath the back end of the car. Flow simulations were used to determine that the best course of action was to use a spoiler, which provided no extra lift going backwards, yet provided the extra desired downforce. A deck lid fin and deployment flaps on the roof were added to keep the cars from liftoff during a crash by reducing undesired low pressure zones that cause flipping. Flow simulation can identify areas of low pressure versus high pressure and help design wings and airfoils for common vehicle types. By comparing the difference of pressure using a cut plot and the surface goal forces to calculate lift and drag together, a design can be aerodynamically optimized. Checking the difference between a car going forwards and backwards, you can calculate if an accidental turnaround would incite a car to lift off of the ground at high speeds, and you can design against it. This is how flow simulation can help designers put the force on their side.